Okay, so welcome back, everyone. So we introduced this concept of homogeneous coordinates. Just to recap, we said if we put zeros and one and all zeros and one in the bottom of our matrices and extend our vector framework by denoting vectors that represent a location with a 1 at the end in the third coordinate or the higher level coordinate, and vectors that represent a vector or a direction with a 0 in the last coordinate, then we can use the matrix multiplication to do translation also. And we can still use it to do all these linear transformations, of course. So everything fits into one framework, which we can see here in an example. This is the combination of scaling and moving. So we have a vector or a vector representing a position or an object like a corner of a triangle, the vertex of a triangle. And then we multiply with a scaling matrix. So we scale it to a new position, and then we apply a translation matrix, then we translate it, and we know that we can also compose those matrices and get one operation out of it. And if we do the matrix multiplication, you see that you end up with this matrix here, and we apply it then to this location. We see we get exactly what we want. We get the x and the y values scaled, and then we get them translated, which gives us exactly this vector that we end up here. And we also see if we apply the very same matrix to a vector not representing a location, but a vector representing a vector or a direction and a length. If we apply the very same matrix to it, because we have this 0 here in the third coordinate of the vector, you see you get what you would expect. You get the scaling operation, because that's an operation that you can do with a vector, because you just scale the length of the vector, but you do not translate the vector, because the vector is defined by a length and a direction and not by a position. So translation doesn't make sense, and you see that works out. So the homogeneous coordinates fit in this whole framework, and we can do our calculation just the regular way that we're doing it. We just have to have this additional dimension, which from 2D to 3D means we have to go to calculation with 3x3 matrices now. Good. So let's look at an example. I mean, the original reason why we came up. Yeah. That's I think what you're asking is a little related to this terminology. I already realized I have to explain this differently next year. I think it's a little confusing what I said at the beginning. Vectors can represent locations, but they can also represent like a real vector, which is an abstract concept. And that is exactly the point. If you have in your program a vector that represents just a length and a direction, and then you can use that for all kind of things, and then you can also transform this vector. You can say, I want to make this vector larger, scale it by a factor of 2, and then you want to multiply it with the matrix. So you need something to apply these linear transformations to it, but you don't need something to translate it, because the vector you treat it as an abstract concept. Only if you use it then to describe, for example, like here on the board, a triangle, or point or vertex on the triangle, then you have a location associated with it or point with it, and then it can be translated. And what do you mean? What you mean in this example? That was just to illustrate how it fits. You don't have to do this in a concrete example. That was just to illustrate that there is no that it fits, that if we multiply the same matrix. Of course, if you know you have a vector and you just want to scale it, you wouldn't multiply it with that matrix. It was just to illustrate that if we have a vector and we do it, the framework fits in a way that you cannot translate a vector because we have this 0 at the bottom. Yeah, that was okay. Sorry if I didn't make this clear. Good, because here now we see an example, and there we will see that we are dealing really with positions. We don't dealing with vectors. So this is an example where we want to do a reflection on a line, and so far we had reflections only on a line that was going through the origin. And I think we had the example for x equals y. This is now a line in another direction, but if this line would go through the origin, so if it would be x equals y equals minus x, then it would be a very simple reflection. We would just look at how the x and the y values, they would just change from the sign, but it doesn't go through the origin. So what we could do is we can just translate everything in a way that the line goes through the origin, then do the simple reflection, and then translate everything back. So let's try to do this. We have a line, and we want to translate that, a line y equals minus x plus 5, and we want to translate that to the line y equals minus x. So if we look at what we have to do here, of course we just take each point on a line and subtract 5 from it in the y coordinate and leave the x coordinate unchanged, and then of course we end up with the correct line here that goes through the origin. So the matrix for this would be the 0 value stays unchanged and the y value is minus 5. So if we add this here, we get here 0x, x plus 0, and we get y minus 5. So that would be exactly the matrix that does this transformation for us. So we get the first matrix 0 minus 5 here, and then we do the reflection on this translated line. So we multiply, of course we have to also translate the object with it, so this goes also 5 down, and then we multiply this with the matrix that does the reflection, which is the reflection on xy was what x equals y equals x, the reflection was 0 1 1 0. So remember we said we just swap the coordinates, and in this case if we do a reflection here, if you look at an example, you easily see that we do not swap just the coordinates, but we also change the sign. So this is the reflection matrix, which we can then do as a second step. But since we are now in a higher dimension, we have to add this homogeneous coordinates to it. So the matrix that we get here is, if we multiply this, 0 minus 1 minus 1 0 and 5 0 0 0 1. Good. And now we did the reflection, so we want to push everything back now. Now, of course, from the image, it's immediately clear when we are at the bottom, we do minus 5 to translate it there. Then if we want to push it up, everything back up, then we just add 5. But of course, we have done the reflection here now. So this object that we moved here is now here after we applied the reflection matrix to it. So if we move that up by 5, you see that we end up at the same at the target position. So we just have to add here 0 and 5 to the matrix, and then we get the correct translation. So if we multiply this here, we get 0 minus 1 minus 1 0 5 5 1 0 0. Of course, we can each time apply all the 3 matrices, but we can also compose them and then have this one single matrix that represents our whole operation in one step. Good. So so if we want to create something like this, we can do it by combining the 3 matrices and then multiplying them like I did right now. But we can also, like last time for the linear transformation, we also said, can we come up with the column vectors by just what do the column vectors represent? What are these? And then we've seen that for the linear transformation, the column vectors represent the image of the base vector under the linear transformation, and that is exactly the same case here also. These vectors represent the image of the base vectors under the linear transformation, which means the linear transformation is the one where we move it over here. So we do the mirroring when we move the line here, and then we do the reflection, and you see, of course, they just point in the opposite direction and change their sign. So this is the image of the base vector. So 1, 0 becomes minus 1, 0, becomes 0, minus 1, and 0, minus 1. Here, this is the reflection, of course. And this here becomes minus 1, 0. And of course, because how the translation is defined, that we have here the identity matrix, it is clear that this translation does not change what we have here with the base vectors. So this is why this is still the image of the base vectors under the linear transformation. And these are the homogeneous coordinates that we had to add. And this part here is now the interesting part, because that represents our translation. And you see here, we moved it, we subtracted 5 from the y-coordinate, and then we added 5 to the y-coordinate. So the relation here doesn't seem to be that obvious. But if you look at the image, if you look at where the origin moved, you see it moved to the position 5, 5. So based on the image, you see that this is actually exactly the image of the origin. And if you look at the matrix, I'm not giving a proof here, but if you think about it intuitively, it kind of makes sense, because the origin doesn't change with the linear transformation, because if you do a rotation or something around 0, 0 always stays the same. But but of course, if you do a translation, then the origin changes. So if you do a translation, the origin changes, and then you do the reflection, and then of course you get the origin on a new position, because you translated it first, and then you move it back, and then you have the image of the origin under this affine transformation. So this is the important difference here, that here, this column vector here, these column vectors here are the column vectors that you get by the linear transformation of the base vectors, and this column vector is the one that you get by the affine transformation. And this here are the homogeneous coordinates. Good. So now we know now how we can use matrix multiplication to transform objects, to do linear transformations and affine transformations, which means we can also translate objects. And like I said, I did this with 2D because the more complicated concepts are easier to understand and to draw, of course, in 2D. But when you understand the 2D case, the 3D case is also straightforward. In most cases, just a straightforward generalization. So let's look into 3D now. And of course, we have already seen a first example for 3D, which was the shearing in XY direction, which I used to illustrate how the homogeneous coordinates can be motivated geometrically. So we've seen here that if we multiply this with an vector x, y, z, then we get x plus dx, y plus dy, z. And of course, we do not have to restrict ourselves to just this last column here. We can also put values here. Then we get here, of course, if we multiply it again with x, y, z, we get here a more general case, x plus dx2, y plus dx3 z, and the same for these here. So we see here, of course, here we put it to 0 because we were not interested in shearing it with respect to the y, with an influence of the y coordinate. In fact, we wanted to get rid of this influence of the variables here, which is why we set the set to 1, and then we just have a constant value here. Actually, that should be set. And but of course, if we do it for a transformation, then we might want to have this influence. So we can do a shearing parallel to the xy plane by setting the variables here, setting constant coordinate coefficients here that are unequal 0. Likewise, we can generalize the homogeneous coordinates to 4D now because we have to go one dimension higher. And of course, that is the part where you really have to explain it in 2D because you cannot draw a 4D shearing. But it is, if you write it down arithmetically, you will see that it's pretty much a straightforward generalization, and it always works out in the same way. If we represent points with a 1 as a fourth coordinate, vectors with a 0 as a fourth coordinate, and again for the matrix, we add this additional row and this additional column, which are all zeros and ones, unless of course we want to do a translation. Then these values here represent the constant values that we need for the translation. Good. So let's look at a couple of examples. Probably the most simple case is like in the 2D, also the scaling. We just set every value to 0 except for the ones in the diagonal, because those are then the ones that are multiplied with this coefficients, and then we get scalar multiple of the coefficient. So if you write this down, this is pretty straightforward. Shearing we already had, but of course now in 3D we have more options. In 2D we could only, like I said, push sideways or push up and down, so we could only shear along the x-axis or along the y-axis. Now we have 3 axes, so we can shear along 3 axes, but we can also shear along combination of 2, and we already seen this previous example. We sheared along the y and the x-axis, so we were shearing along a plane, but we can also shear just in one direction, for example like here in the x direction, also in the y direction. So you can make up all the other cases for yourself. So we see we have more options here because we are in 3D, but the basic concept is pretty much the same. And that's also true for reflection and rotation. The basic idea is the same, but we have more options. So for example, the reflection that we did so far with respect to a line, the most straightforward generalization to 3D would be, of course, a reflection along a plane with respect to a plane. Of course, we can also do a reflection with respect to a line in 3D in the same way as we could do a reflection with respect to a point in 2D. You have line and point reflection in 2D. In 3D, you have plane, line, and point reflection. Plane is, of course, the most common way, but reflection with a line would also be possible. And rotation we did in 1D is in 2D we did it around a point, whereas in 2D you usually do it along a directed line. Of course, we can also do it in different ways, but the most common way is along a directed line. Now, of course, you probably wonder what is a directed line. So let's look at an example. Let's first look at a very simple example, which is rotation around one of the axes. Let's say around the x-axis, the y-axis, the z-axis. To understand this, let's look at, because we already know how to do a rotation around the origin in 2D. So let's look at that case and then try to come up with how we do a rotation in 3D. If you look at the 2D case, so if we see this as the xy plane and this 2D, so we forget about this one, and then we do a rotation here counterclockwise around the angle phi, then we see here, if we compare this with the 3D case where we do a rotation around the z-axis also with the angle phi, we see that the xy values actually behave in exactly the same way as if we rotate in the plane. And the z value we see stays the same because we are rotating around the z-axis. So the values don't move up and down, they stay in the same plane. So they keep the same value. So what we get here is for the x and y values, we get the very same matrix as here. And then we just have to fill it up for the z value with something that doesn't change the z value, that keeps it the same. And we already had that with the homogeneous coordinates because we introduced them in a way that they don't change anything if we don't want to translate. So we just put everything to 0 except for this value here, which is 1, which then just copies the z value. So this looks, of course, the same as the homogeneous coordinates because the motivation is the same. We want to have an additional line or additional row that doesn't change the value, but of course it's a different motivation. So if we do homogeneous coordinates, if we also want to do this combine this with translation, we get another row here because we're in 3D, so the homogeneous coordinates are then now 4x4 matrices. Good. So now, of course, the more interesting case is how can we rotate an object or a vector around at a certain angle around a random line or a random vector. So the directed line or the directed in a line means that we're looking at the vector around which we are rotating, and that of course for the rotation itself doesn't make a difference. So if I have a vector like this and I rotate around it, or if I have a vector like this and I rotate around it, the result is the same because the line it represents is the same, but the way we're doing the calculation now is from the way we're doing the calculation now, the direction of the vector is important, and that's why it is called a directed line here. And the idea is basically, again, combine the more decompose the more complex operation into smaller, simpler, and easy doable operations. And of course, we already learned how to rotate around the z-axis. So the natural way to do this, or the most obvious way to do this, if we know how to rotate an axis around an axis, and we know how to rotate around the origin, then the most straightforward case is, of course, take the vector and everything else and rotate it in a way that it matches the z-axis, then do the rotation around the z-axis of everything, and then rotate everything back. And if this is, for example, our rotation matrix 1, and this is the rotation matrix 2, then this is, of course, just the reverse of it, or the inverse matrix of it. So I hope you see now why I said at the beginning inverse matrices are very important when we do transformations, because that way we can easily do this more complex operation. Good. Now, of course, we have to rotate everything back and forth, so we have to take all things here, not just this vector, but also this here, and that is, of course, a little more difficult. I mean, the rotation around the z-axis, that's the simple case. We already know that. The question now is, how do we get the rotation from everything to the origin and then everything back? Now, the back way is also very simple, because if you remember what the columns of this rotation matrix represent, so the rotation is a linear transformation. So remember, the columns of the rotation matrix represent the image of the Cartesian basis vectors under the transformation. Now, if you think about what we do here, if we want to transform everything and map this vector here, that means we have a coordinate system here. We move that coordinate system that it matches this coordinate system here, and then also, of course, all the points with respect to that coordinate system. So this cube is somewhere here. And then we rotate everything, and then we move it back to this coordinate system. But that means if that is the image of the linear transformation of the base vectors, and we move it to the original base vectors, then of course this image are the original base vectors. So if we call these vectors, for example, v, w, and u, then of course these are just the column vectors of our reversed matrix. So you see here, these are the base vectors, then we do the rotation, and then of course we end up with these vectors again. Now, the other question is, of course, what is the original rotation? Now, we could just do the inverse of that one, but if you remember when we introduced the coordinate systems, I said there is also a special case, which is the orthonormal basis, which means that the vectors are perpendicular to each other, the base vectors, and they're also unit vectors, so they have a length of 1. And I said that this is very often very useful and very handy, and this is one of the examples for it, because if that condition is fulfilled, then we can prove that the inverse of an orthogonal matrix, that is the matrix that has these vectors as column vectors, is just its transposed. So we just take this matrix here, we don't even have to calculate the inverse, we can just write it down and just put the transposed vectors here. So you see, this is pretty simple, pretty straightforward. The only problem is, of course, we don't have this coordinate system here, we just have one vector, and so we need to represent this coordinate system, and it has to be an orthogonal coordinate system where each an orthonormal basis, so each vector has to have the length 1, and they all have to be perpendicular to each other. So how do we do this? If in 2D, you should already know this, because you remember we calculated normal vectors to a line in 2D, so we know how to get an orthogonal vector to a two-dimensional vector. But in 3D, you also know how to get orthogonal vectors by doing the scalar product, the cross product. But for the cross product, you need two vectors. Now here we just have one. If we had two vectors, we could easily create a third one that is orthogonal to it. So how do we do that? The trick is just we introduce some dummy vector, just a vector that is called, for example, we can call it t, and there has to be a certain angle alpha, and that alpha doesn't have to be a right angle, it can just be any angle, which is why I called it a dummy vector, because we just have to create a vector that is not parallel to the original vector, because then we can multiply it with the original vector and we get a vector that is perpendicular to it. So the first step is we create dummy vector t that is not parallel to the vector w, because if it is not parallel to w, we can multiply it with w and get a vector u. Let's call it u. We can do the cross product, and then we get a vector u, which is then at a right angle to the original vector w. It's also at a right angle to the vector t, but since we're not interested in it, I mean, there's a reason why I called it dummy vector. This is the important thing. So we have two vectors that are orthogonal to each other, and we need three, so we just multiply this result here again with the vector w, and then we have our vector v, which is not only orthogonal to v, but also to w, but also orthogonal to u, and also the other way around. So we have here our created our coordinate system with these vectors here that have the right angle. And then the only thing we have to do is, of course, the normalization, which means we have to multiply it with 1 divided by the length of each vector. We have to multiply with to divide by its own length to have a unit vector. And when we have that, then we have an orthonormal basis of a coordinate system. And then with this operation, we can move it to the origin. We can map that to the original coordinate system. We can easily do the rotation around the z-axis, and then we just rotate it back to the original position, and then we have done our transformation. And of course, since this construction of this coordinate system was using this dummy vector, which I said can be any vector as long as it's not parallel to the vector w, because then of course the cross product doesn't work, but it can be any vector. That means, of course, we can have an infinite number of coordinate systems here. But if you think about it, of course, it doesn't really matter, because if we, for example, do the rotation in a way that we map, like in this way, R1, where we map it that the cube fit is on this corner, or in that case here, where the cube is on that corner, R2, And now we do the rotation r phi around the z-axis in both cases. That, for example, the cube is then here or here. If we do here the reversed operation, again, of course we end up with the same. Where do I have to draw it? Here now. The cube is always at this position because, of course, we're having a different mapping here, but the rotation stays the same. So if we do the correct inverse operation, we end up with the very same image. So it is not unique, but it doesn't have to be unique. Good. Yeah. So let's look at an example of reflections. Remember what we did in 2D. In 2D, when we wanted to do we wanted to do a reflection with a line. We looked at the line y equals x, and then we figured out how the reflection matrix looks like by just looking at what happens to the coordinates when we do it, and then we see that they were just swapped with each other. So if we want to do this in 3D, for example, at the xy plane, let's look at how a reflection there changes the coordinates. And if you look at this image, you see that the x and the y coordinates don't change when you do a reflection. The x and the y always stays the same. The only thing that changes is the z coordinate, and that changes just by changing the sign. So from z it goes to minus z and the other way around. So what we see here is that we can do this with a matrix where we have the x and the y value unchanged, and so we do the identity here, and then the z value just changes its sign, so we multiply it with -1. And again, if we also want to use this in relation to an operation that includes translation, then we of course also have to add the homogeneous coordinates here, and it looks like this. Good, so this is pretty simple. It's more complex, of course, if we do a reflection on a random plane that is not the xy plane. So let's first look at a plane that is random but is still going through the origin. And I will also not do this in detail because that's a lot of calculation here, and I think I already had a lot of material today. I will just tell you the idea of it, and then in the tutorials you will have a similar case but with 2D, which is of course easier to write and easier to calculate. But I want to give you an idea about how this works, because otherwise it will be you'll probably have difficulties with the tutorials. But I think it's better to understand if I don't overwhelm you with too much stuff today and you try it yourself. Good. So so what can we do if we have this this representation of a plane and we want to reflect our vectors here, and we want to have the matrix that represents this reflection? Now remember, we have a reflection is a linear transformation. For a linear transformation, the column vectors of the matrix are the images, represent the images of the base vectors. So if I draw this, I'm trying to draw it in 2D version of 3D now. If this is our base, so this is the base vector b1 is 1, 0, 0. This is our base vector b2 or b3, which is 0, 0, 1. And this is coming out of the screen, our vector b2 equals 0, 1, 0. And now we have a plane that goes through the origin. So if we have that doesn't go through the origin. That works. If this is the cut through, then of course it looks like a line that intersects with this b1, b3 plane. And now if you want to get the image, that was actually a bad plane because it's at an angle of 45 degrees, and it's harder to draw or harder to understand when I draw it. Let's say this is our plane, and then of course we want the image of that vector here, so that means we have to reflect it here to this position b1, and then we get b1 dash, and that is then the first column of our matrix. Now there are that's why I'm not doing it here, because in 3D this is very complex, and also in 2D without me telling you what is a way to do this, it will probably be too difficult for you in the tutorials. How you could do this, for example, is you could, to get the image of this vector here, if it is not obvious, like here in this case, like the previous case, we had x equals y, and then it was obvious how the other coordinates look like. But if you look at here, at least for me, it is not obvious to see how it looks like. I have to calculate this. And one way you could do this, you have the normal vector on this plane here. And you have this vector b, so you can use these two to construct a line here in parametric representation, which means you take b1 as the support vector, n or minus n as the direction vector, and then you can calculate the intersection of this line with this plane here. Then you have the intersection point here, and you have the t, the parameter for this intersection point. Now, since this is a reflection, of course this distance here to the top is twice as much as the distance here, so you just multiply the parameter t with 2, and then you can calculate this value b1. An alternative solution would be to use what we have done also with the other thing. In the other case, if again this is our b2, b3, b1, and this is our plane that goes through it, you can rotate that plane by an angle phi, so it intersects with the b1 axis, and then you can rotate it in 3D by another angle that it also intersects with the b2 axis, and then you can do a reflection with this xy plane, or b1, b2 plane in that case, and then you just have to rotate it back. And if you do that, it is a little more complicated in 3D, because in 2D you can easily use the triangle relation, which you can see when you draw it. Of course, you can also use the trigonometric triangle relation in 3D, but it's not that easy to draw, and therefore not that easy to get. But if you do that, you get then the matrix. First you rotate everything to B1, then you rotate everything that's in line with B2, then you do the reflection, then you rotate it back, then you rotate this one back, rotate it back, so I have to use the inverse matrix here, and then you have it. So it looks complicated, but you have to only create this once, and then you have one matrix that represents this transformation. Of course, that is also the solution how you could do it when you have want to do a reflection in a random plane that does not go through the origin. Then you can just use the translation to do it here. So if you look at this framework here, you just have to do a translation first, then you do the whole reflection like we did it here, and then you do the reverse operation of the translation again. And one of the reasons why I also wanted to write this example down is to again illustrate why these homogeneous coordinates, which at first seem a little complicated or out of, I mean, we're talking about 4 dimensions here, so it's hard, you cannot imagine that visually anymore. But if you think about it, here we want to have this complex operation. We just have to create this one matrix, which is composed out of 7 individual matrices. We just have to create that once, and then we have a single matrix that we can use to do this transformation. If we would not represent translation with a matrix multiplication, but we do it with vector addition, we have to do this transformation each time. We have to apply these multiple transformations to it, because we don't have this framework where we can compose everything into one matrix. And that hopefully illustrates now why this is really a good thing, and not only because the hardware only supports matrix multiplication. I mean, the hardware only supports matrix multiplication because we can also do it with matrix multiplication. Good. So yeah, then I'm at the end for today.